All right, welcome to lecture 10 for machine learning 2. Today we're going to talk about a span, vector space, row, column space, various spaces. So let's start with the concept of a set. A set is a collection of distinct elements. Okay? And we mathematically denote the concept of a set with braces like this, brackets. Now, anything can go inside a set. For example, dog, cat, fish, bird, set of animals. Notice they're distinct. Okay? You can also have a set of flags, so emoji flags, or a set of numbers. Okay? If there's nothing in the set, nothing, notice how we use the brackets as the notation for set. Then if there's nothing, we call this an empty set. A set is symbolically represented with a capital cursive letter like this. Right? So a set is equal to some elements inside the set. So it could be cursive, capital, and these represent the concept of a set. Now, space. So we just talked about set. Now, space is a set with certain defined properties. So this is a set, this is a set, this is a set. So these are sets. The difference between a set and a space is that in a space, there are certain properties that's predefined. So, for example, let's say we have a set of flags. Well, how do you know how to add two flags together? Well, you don't because it's not defined, right? There's not a space that defines it. But once you define it, then that becomes a space. So this is where the concept of space comes in. The space is a set where certain structures are predefined. So, for example, like we don't know how to add this right now, but I'm going to define it now. And this is the addition of these two is equal to the summation of the population of the two countries. And I'm going to call the space Wu space, Professor Wu space. So previously we had a set, right? It was not defined. Therefore, without any definition, we don't know. We don't know how to add two things together. But as soon as I define it, define the meaning of some kind of structure for addition, a set is now a space. And we have a name for the space. Depending on what you name it, it has different properties. We call it Wu space. And within the Wu space, these symbols make sense. Another way to define a set is by a vector. So let's say we have a vector 1, 1, like this. This is a vector 1, 1. With a vector 1, 1, we can essentially define a space as all the possible points that could be reached by 1, 1. So if you have this vector, let's see if I can. Yeah, if you have this vector, well, depending on how you stretch it or shrink it or taking the opposite, right? Then the space defined by this vector is defined by all the possible points you can reach by stretching this particular vector. So you can imagine this vector is 1, 1. Therefore, the point 2, 2, you will need to stretch it. So that's what it means. That's what it means that a vector can define a space. Right? You have a vector and all the possible points reachable by this vector by scaling is a space. Now, this space has a special name. Space span that's reachable by a vector is called span. So when we talk about span, that's a space created by vectors. Okay? So, for example, 1, 1 is in the span of this because you can reach it. 2, 2 is also in the span because if you just multiply 1, 1, you stretch it a little bit, then you can reach this point 2. 0.3. So in this particular case, 0.3, you need to like squeeze it. or -10. You got to go in the opposite direction. So these are the span. This line is the span. All the points reachable by this vector. However, if you have a point outside, right, no matter how you stretch this vector, you can never ever reach this point. Now, this example is much better understood through this example. So let's say the concept of span is best explained with an analogy. Okay, let's say we have a student. Let's say we have a boy. We'll make this boy Alex, and Alex really likes a girl, Anushka. Anushka. Okay, so Alex likes Anushka, and one day Alex sees her in a party. So Alex decides to walk up to her and try to get her phone number. Okay, so the target, the goal, is to get her phone number. Now, the student never really talks. Alex never really talks to girls, but he read somewhere that flattery just might work. Right? So we're gonna so he has one tool in his tool belt, which is flattery, and we're going to mathematically represent the concept of flattery as a vector. All right, 1, 0. So this right here is the concept of flattery. Of course, you can flatter them half, give a half of flattery, or you can go opposite direction, give her insult, or you can give her flattery twice. So, so flattery X right now is the only strategy, right? The student can extend this technique, right? Give more flattery or less flattery, represent as the vector multiplied by some number. So, for example, if you have alpha time equals to 2, that means you would give the girl 2 compliments. Okay? And if you were to have a -1, it would be an insult. Now, according to the top right figure, like right now, the vector looks like this. How many compliments would be required to get her phone number? So her heart is here. So if this is at 1 and this is at 2, first of all, can flattery and compliments reach her heart? Well, yes, you can. And this is at 2. This implies that if you give her 2 compliments, you can get her number. Okay? And when this happens, it means that her heart is in the span, is in the span, is in the space of possible points you can reach by stretching what you can do. So, so this means that the target, her heart, is in the span of the vector x. So when we talk about span, if something is within the span, it means that the vector can reach it. By using whatever tool you have, you can accomplish your goal, for example. Right? Conversely, let's look at this example, the bottom one. In this case, can you stretch, give her multiple compliments, right? And be able to reach her heart? The answer is no, because her heart in this particular case is not in the span. Like the span is only this line here, right? So her heart is not in the span of the vector. Therefore, flattery alone, like you need to go somehow in this direction. Just flattery alone will never reach her heart. And essentially Alex will never get Anushka's phone number, no matter how many flatteries you do. So it's outside of Alex's ability. Therefore, the heart in this case is not in the span. Right. Let's expand the tool set. So after not getting the phone number, Alex goes back to drawing board and learns two more techniques. Two more techniques. These two techniques, one is called humor and the other is called flirting. Okay? We're going to represent humor as 0, 1. So this vector here. and flirting as 2, 1, this vector here. So note that humor and complement are independent. So complement is going this way, humor is going this way. This implies that no matter how much humor you have, you can never create a complement. And vice versa. No matter how many complements you have, you can't create humor. So those two are distinct concepts. And you can see this that no matter how you extend or stretch humor, you can never ever create a complement, right? You can never use this to create this. Vice versa, no matter how many complements multiplied by any number alpha, this vector multiplied by any alpha, you can never ever achieve humor. All right. The other technique is called flirting. So this vector here is flirting. Now, flirting is a combination of complements and humor. So you have complements and humor. Mostly because flirting is some complement, but apparently a lot of humor. So according to this, you have one complement and two humor, right? Which means, yeah, you need is it one humor? Yeah, I have it backwards. It's actually one complement, two humor. One complement, two humor. Okay, so flirting is a combination of compliment and humor. Now, given this new set of tools, now that you have three tools in the tool belt, can the boy reach the girl's heart? Can you reach the heart now by certain combination of three of them? And what combination will be required? Okay? So you can see if you do 1.2 complement and zero point 0.6 humor, right? 0.6, you will be able to reach a heart. So, or you could do certain amount of compliments and then certain amount of flirting, right? Flirting goes this way. So, certain amount of flirting, you can also reach a heart. So, now in this case, because you expanded your tool set, you have now a higher capability and you can reach a heart using the tools available to you. So let's try to understand this concepts of span, right? In this case, the heart is now in the span. It previously wasn't when all you had was complements. But now, because you added other dimensions to your tool set, you can reach the heart. Now imagine we can represent all the tools available to us to achieve a target as different vectors. So imagine all the tools you have are vectors. Mathematically speaking, we call these vectors the bases. So if we have three tools, it will be three bases, vectors. And together, we can represent that as a matrix. So these are the tools available to you. Now, everybody has a different set of bases. You can imagine you are good at certain things, and I'm better at certain things. So we have different tools. And your current basis essentially defines every possible thing you can achieve, right? Depending, like right now, because you have three tools, how you use and stretch these three tools will allow you to reach the target. So no matter what the task is, you can imagine that we can represent the tools as vectors, and we can represent the target as a point in space which we're trying to reach using the tool we have, right? It doesn't matter which task, we can always represent these tasks mathematically as a target. And we can say this target is winning a basketball, right? So winning a basketball game is a point in space. How do you reach that point? Or you want to get a job, how do you reach that point? Essentially, anything you want to accomplish in life could be modeled as a point in space. Getting her phone number, a point in space, right? Getting rich, a point in space. All these are just points in space you're trying to reach, right? Now, by using different proportion of the tools available to you, you can achieve the target, right? If you can achieve the target, then the target is within the span of bases. It's within the realm of possibility. But no matter what you do, you cannot achieve the target, then the target is not within the span of the bases. The concept of the span is a set, right? It's a set where what's inside a set is every possible combination of things you can achieve given the tools, given the bases that you have. Okay? So no matter how hard you try, how close you come to the target, there will always be an error between what you can achieve and the target itself. If the target is not within the span. So if it's not within the span, you can never ever achieve it. And this is a mathematical certainty. Okay? Now, you can have redundant bases. So notice how we could have used flirt and humor, right? We could have used flirting and humor to essentially reach the heart. What would we have to do? Let's see. We would have to be more serious. We got to be a little bit more serious, which is the opposite of humor, I think. Serious. And then you need to do lots of flirting. If you do that, this combination, you'll be able to reach your heart, right? So we can use combination humor, flirting, or we could use compliments and humor. So compliments, humor. This is much easier. So compliment will go here, humor goes here. We reach the heart. Notice that when we only had complements, the space we span was only one dimension. So when we had complement, this is the space we span, right? After adding humor, if we have complement and humor, now the space is this entire 2D dimension. Therefore, when we add flirting, it doesn't really change anything. All the possibilities are still just 2D dimension. So just because we have three tools available to us, three tools, it doesn't mean that the space which we span is three dimension. You could have redundant abilities, redundant bases. So flirting is redundant because you can always use some combination of human complement to reach the heart, right? So flirting in this case is a redundant basis. Now, when you have n bases, the maximum dimension, so if you have three, the maximum would be three. Every one of them could be creating a new dimension. Or it could be something significantly less than three, right? So you have three vectors, but you only spans two dimensions because there's redundant. However, depending on the number of redundant vectors, the space spanned by n bases could be much smaller. So that's what that's saying. It could, just because you have three vectors, it doesn't mean you can span three dimensions, right? The number of dimensions spanned by the bases is called the rank. So rank, that's what the rank means. So right now, we have three basis vectors, but the rank is equal to 2. Okay? Given a matrix defined by a set of basis vectors, the rank of V is the number of dimensions spanned by the basis vector. Okay? So this is it. All right. So the conclusion, if you conceptually understand, can grasp the concept of span. The span is the space of possible points you can reach, right? Span of possible targets you can achieve. So the conclusion from understanding span is that you can achieve anything. You can achieve anything that is within the span of the tools, the vectors available to you. So if you have the tools, you just have to put in the work, right, to reach the target. It is not always obvious in life what combination of tools you're supposed to use, right? So you could have lots of tools, but you don't really know which one you should use all the time. It's not that obvious, and and this is because we may have a lot of redundant tools, right? So in this particular case, you could reach the heart many ways, and that's because you have lots of redundant tools. Now, in this particular case, we only have three tools. But you can imagine in your own life, you could end up having lots and lots of redundant tools that can, doing different combinations of different things, can achieve the same result. So it's really hard to know how much repetition of each tool is you're supposed to use and what proportion of effort is required to achieve your tools. So here's vector tool one, tool two, tool three. These are vectors. And here's your target. How do you know which alpha to pick to reach your target, right? And by knowing the alpha, like you will essentially know the proportion. What is the proportion effort that you apply each tool to allow you to reach your ultimate goal? So in mathematics, we know how to do this. In real life, it's much harder. It's you don't really always know how much effort you're supposed to exert in various parts of your life. Now, sometimes the alpha value could be very, very large. So you have to repeat whatever you do over and over and over again until you reach the sufficient alpha value. And very few people will be willing to put in enough reps to achieve it. So this could be like 1,000. So you have to repeat the same thing over and over again 1,000 times to achieve your target. So it is really easy to and fun to talk about what you want all day. It is not fun and a lot of work to generate these alpha values that will ultimately impact your life. So once you understand the concept of span, this right here kind of mathematically describes what you're doing with your life. Right? We all have certain tools and we have some goals which we're trying to achieve. Right? And and this right here is the math that describes that. Now, if there's so many uncertainties on how to achieve your target, what's Professor Wu's personal strategy of finding the alpha value? Well, the answer is gradient descent. You kind of look at where you are and where you want to go. Do you want to go up or do you want to go down? And you just walk that direction, one step at a time. Believe it or not, this is literally how I work with my life. Okay, so now that we have some conclusion, let's look at the inverse, the converse conclusion. So conversely, we would just talked about what you can achieve. Now we talk about you cannot achieve anything that is outside of the span, right? So if a heart is here and you're going that direction, no matter how far you go, you can never achieve the point. So if it's outside of the span of your basis, it's outside of possibility, the realm of what you can achieve. However, what is interesting in life is that your basis vectors are constantly changing. So just because right now you only have one tool, maybe tomorrow you have two, and suddenly the total dimension you cover is no longer one dimension, but two dimensions, right? So you can imagine you're constantly building your basis so that you're spanning a larger and larger space. Well, every time you make a new friend, right, that new friend is a basis, is a new vector. Every time you grasp a new concept, right, you added a new vector. As you add more and more vectors, the rank of your span will over time increase. So that's how you increase in your capability by learning, by getting to know more friends. By doing these things, you are expanding, increasing the span of the realm of possibility. Remember, span is the space of all the possible things you can achieve. And by increasing the rank, increasing the total dimension, you are drastically increasing of the possibility of what you can achieve. You can imagine when you were just a baby, right? You only really have one tool available to you to influence your surrounding, which was crying. So that was one tool. You can cry more, you can cry less. All right. So if you were able to influence your surrounding by crying, that's one dimension. You can imagine now the rank of your span has increased thousands of fold. Your ability to influence your environment has increased so much compared to that baby that only had one single tool. You have many tools now in your tool belt. The concept of span is the mathematical understanding that explains why we're here in the university and ultimately why we're doing anything at all. This is the math that's basically explaining that. We all have a vision. You can imagine we all have a vision where we would like to be one day. And that vision is our target. We would like to be rich. We would like to have a job. We would like to find love, right? We have some kind of vision, and that is our target. And we all have our basis tools, V1, V2, V3. We all have some kind of tools available to us. So in life, what we are doing, ultimately, every one of us are doing, is just that we're expanding the rank of our basis. We're constantly trying to expand the rank and finding the alpha values that gets us to our goal. All right. You we're That's all we're doing. We're either expanding our bases, uh, the rank of our bases, or we're finding the alpha value to get us where we want. Okay. So now that we have conceptual grasp of the concept of span, the mathematical definition follows very easily. The span of V, right? A V is a bunch of bases. The span of this is a set, right? It's a set of the combinations of the vectors. So, so this notation, I'm going to assume many of you don't know this notation. It's called a set builder notation. So this right here is a set, and then we define what goes inside the set. The way we define the set is this is a set such that you pick alpha 1, alpha 2, alpha 3 from numbers. So if you can pick you pick some kind of alpha 1, alpha 2, alpha 3, plug it in here. That's a single point. You do it again, that's another point. You do this infinite times for every single possible combination. Then you create an infinite size set. And that infinite set essentially tells you every possible point you can reach given these vectors. Okay. Now remember, span is a vector space created with bases. So this is a span. A space is a set of elements with rules. Therefore, the span is a set of elements reachable by the basis. So you can see every possible combination reachable by this is inside this set. Okay. From this definition, it tells us the point U is within the span if there exists some kind of alpha, right, that multiplied by these vectors such that we can achieve U. This is how we know if a point is in the span. If you actually have some alpha values that allows you to reach that point. Okay? If we want to know if a point is within the span, we simply have to find the alpha value. So if you find the alpha value and the result is equal to U, then U is inside the span. How do we identify if a point is within the span? So we just talked about that, right? So here, let's say we have these as our basis vectors. These are all the tools we have in our tool belt. And this is the point we're trying to reach. So what it's saying is that there are some weights that we have that multiply each vector that allows us to achieve this. So if we know if there exists a set of weights that allows us to achieve this, then it's in the span. Okay. Now we can rewrite this expression. We pull out W1, W3, and that multiplied by this matrix will give us 2, 1. I'm going to represent this matrix as A, this is W, this is Y. All we have to do is solve for W. We've done this many times, right? If you can solve for W and the result of W multiplied by A is equal to Y, that means it's within the span, right? We can solve this many ways, like closed form solution. You may have remember from that. We can solve gradient descent to see if it comes close enough, or you can solve it from REF. Okay, let's quickly review how we might solve this. So here's the closed form solution. Well, remember, with a closed form solution here, you could simply multiply by A transpose A on both sides, and then you multiply the whole thing out. So after you multiply A transpose on both sides, you multiply by the inverse on both sides. Well, the inverse is useful because this cancels out, leaving us W is equal to this. So we can calculate for W very easily simply by using this. Now, sometimes we may end up with a matrix that we can't find the inverse. In those cases, if you have a matrix which you can't do the inverse, all you have to do is add a little bit of noise to the matrix. So this is you this delta is a very small number, like zero point 0.1, for example, and multiplied by identity. So matrix plus matrix. This right here will guarantee that you will be able to get a solution out of this. Okay. And you can see right here, right? I took the inverse of this thing multiplied by A transpose and Y. It gives us the weight. And the weight is very, very close to the actual solution itself, which is 2 and 1. Okay? You see? So remember, 2, 1 was Y. So we wanted them to match. Okay. Of course, you can also do gradient descent. So with gradient descent, all you need to do is find, if you want to solve this is equal to this with gradient descent, you simply need to minimize the following objective. So if you want them the same, you want the error between them, square, to be as small as possible. So to find gradient descent of this, you just find the derivative of this. The derivative turns out to be like this. Okay. So once you have the derivative, you run the minimization gradient descent, and you will see that you'll be able to reach the same result. Okay. So now that we understand, hopefully we understand the concept of basis, certain bases we use makes finding alpha easier. You may have noticed that it's easier to identify alpha when we have perpendicular bases, right? When we want to get to a heart, it was much easier to use complement and humor because you can just see exactly how far you need to go. So complement and humor are perpendicular. However, imagine when we're doing complement uh, in contrast with using humor and flirting, right? What combination of the two of them can reach the heart, right? It's not as easy as complement and humor. Complement and humor is really easy. Instead, you want to use humor and flirting, you need to go a little negative and then go up again. So this is an example. This is an example of why when the bases are perpendicular to each other, it's just a lot easier to find the alpha value. In general, we really, really like perpendicular basis vectors. When the basis vectors are perpendicular in 2D, they're called perpendicular. They're independent of each other, meaning that you can't have one create the other one. So they're independent. And we really like it because it makes our life easier. In two dimension, this concept is called perpendicular. But in general, when you have higher dimension, 2, 3, 4, 10 dimension, perpendicular things are called orthogonal. So when vectors are orthogonal, that's when you have this shape. But it could be in very, very high dimensions. Moreover, so we like them to be orthogonal to each other, and we like them to be size 1. When it's size 1, we know exactly how far we're supposed to go. Over here, it will be 1.2, so we just need to go 1.2 times, right? This number just happens to match exactly how far you're supposed to go. So in conclusion, to make finding alpha easier, we really like basis vectors that are orthogonal. Remember, that's when they're perpendicular. Also, we like the basis vector to be normalized to length of 1. When it's normalized to the length of 1, we know exactly how much we multiply by to reach your final destination. And these basis vectors that are both orthogonal or normalized are called orthonormal basis vectors. Okay? Now, we can easily identify if vectors are orthogonal. Right? If you have two vectors, how do you know if they're orthogonal to each other? Like perpendicular. Now, in 2D, you can draw them, but in very high dimension, it's not as obvious. So, what is the equation? Well, two vectors are orthogonal to each other when, if you dot them together, take the dot product between them, you get a 0. So, you can kind of imagine You have this here and this here, right? So this is 1, 0. This is 0, 1. So they're obviously perpendicular to each other. Now, if you dot them together, notice how that's 0. And this relationship holds even if you rotate it like this, right? Over here, I think I rotated it. So this is the rotate version. And when you dot them together, you still get a 0. Okay? In general, we prefer orthonormal bases. We explained to you why. And the way you can tell if you have an orthonormal basis is you simply align the basis vectors here and then multiply them out. X transpose X. If it's orthonormal basis, you should get an identity matrix out. Okay? You can see why, right? X is equal to X 1 transpose X2 transpose. So that's X. Therefore, X transpose X is equal to X. Did I do this right? No. X here is defined as X1, X2. So this is capital X. And therefore, X transpose X is equal to X1 transpose X2 transpose times X1, X2. And if you multiply this out, right, it's equivalent to X1 transpose X1, X2 transpose X1, X1 transpose X2, X2 transpose X2. Well, since they're orthogonal with each other, this would be 0, this would be 0. Like, you remember, when two vectors are orthogonal, they would be 0. And if they're orthonormal, when you multiply by itself, the length is just 1. That's why you end up with an identity matrix. So the way you can test if a set of bases are orthonormal is you stack them and then you multiply them together. And if the result is identity, then you have an orthonormal basis. Okay. All right, so that's basically it for today. The final exercise for you today is to practice this concept. Let's say you have 3 basis vectors. Find the normalized version of each one of them by hand, and then find it with Python again. And then check if V1 is orthogonal to V2, if the two of them are orthogonal. Identify a normalized vector that is orthogonal to V1. So this is V1. See if you can find a vector that's orthogonal to it. And then use both closed form solution and gradient descent in Python to see if the following 2 vectors are within the span. So now these are the bases. See if this right here is within the span of this. And then see if this is within the span of this. Okay? Even though we have 3 column vectors, what is the dimension spanned by the 3 vectors? Okay? So take your time. Make sure you can solve this. And I will see you in the next lecture.